Hello again everybody. In this video we'll be generating fake anime characters using DCGANs, which stands for Deep Convolutional Generative Adversarial Network. So as of now, obviously a lot of development has been done for generative models. Like some papers suggest to implement the adversarial training with different objective functions, and some papers do analysis on these objective functions and then proposes some techniques to ultimately just make the adversarial training faster. But for this video I'm gonna stick to a very special paper that essentially provided a lot of boost for image generation. So before this paper came out, there were many discussions that even though we have many objective functions for improving the adversarial training, but still the majority of the implementation that affects the final outputs of the generator is actually the hyperparameters and the actual architecture of the discriminator and generator. The authors of this particular paper essentially is trying to address this particular problem of finding a stable architecture for generator and discriminator. So they actually did extensive model exploration and finally came to a number of guidelines to follow for implementing GANs for image generation. Alright, so enough talk and let's dig in. And by the way, in case you don't know, one of the author of this paper, Soumit Chintala, is one of the co-creator of PyTorch. So basically he wrote one of the very first code for the creation of PyTorch, and today we are implementing his paper in his framework. Yeah, I think it's pretty cool. Alright, so I'm just gonna share the important takeaway from the paper. So the very first point that they proposes is not to use any pooling layer like max or average, but instead use strided convolutions in discriminator. And similarly in generator as well, any upsampling layer like bilinear or cubic upsampling should be replaced by strided deconvolutions. So the idea behind this point is to allow both the models to learn their own downsampling and upsampling procedure. Now I just want to clear out that it's not like that the downsampling or upsampling layers with trainable parameters are better than without any trainable parameters, because like max and average pooling works pretty great with CNNs in classification models. It's just a fact that the authors found that if generator and discriminator are allowed to learn their own upsampling and downsampling layer, then the training would be much more stable and ultimately generator would be able to produce better images. Okay, so in the second point they suggested to remove any kind of fully connectable layer at the end of the discriminator. So basically they are suggesting to use a CNN layer in order to produce the logits from the discriminator, which would be a scalar for a single input. In the third point, they are suggesting to use batchnorm in both the models, and they found batchnorm to be highly effective for stabilizing the training for deeper models, especially because batchnorm is actually able to solve the poor initialization problem and also helps to provide stable gradient flow for bigger models. And not only that, but they also found that batchnorm is one of the most critical approach for preventing mode collapse, which basically is a situation when the outputs of the generator becomes very much independent to its inputs. So in case of mode collapse, the generator just produces very similar looking images, even though you'd be passing different noise as inputs. And obviously you don't want this. So yeah, batchnorm is just awesome. But there's a point to be noted, as they mentioned here, that directly applying batchnorm to all the layers, however, resulted in sample oscillation and model instability. They avoided this by not applying batchnorm to the generator's output layer and the discriminator's input layer. Okay, so continuing to the fourth point, here they are suggesting to use ReLU activation in generator and LeakyReLU in discriminator. Like you might be wondering what's the logic behind it, and actually there isn't. With just experimentations, the authors observed that using a bounded activation allowed the generator to learn more quickly to saturate and cover the color space of the training distribution. And for discriminator, they just found the LeakyReLU to work well, especially for producing higher resolution images. This actually reminds me of something which I forgot to tell, that we'll be producing images of size 128 cross 128 pixels, so not very typical pixels like 64 cross 64 that you may find in most of the articles online. So yeah, it would be slightly challenging, and let's see how it goes. And actually, whatever the results I'd get, I would have already used it in the intro, so yeah, I think you already know how it will go. Okay, anyways, finally here they mention all the guidelines together. That is like replacing any pooling layer, using batchnorm in both models, replacing fully connected layers, using ReLU in generators, and using LeakyReLU in discriminators. But some additional points are there to mind. First is we'll be using Tanh layer as the generator's final activation, so we would have to scale the real images from -1 to 1, and setting up the beta 1 value to 0.5, which is one of the hyperparameter of Atom Optimizer. And I found that sometimes setting up that value to slightly less than 0.5 also helps, particularly when your dataset is large. Alright, time for the implementation. So first of all, we need a good quality dataset which has fairly good amount of images. And I found this dataset on Kaggle. It has over 60,000 faces, anime faces, and I actually don't like the overall quality of the dataset, but I think its size might just cover for this. So we need this part of the URL in order to download the dataset to Google Colab. And yep, I'll see you there. So first of all, we need to install Kaggle and then upload the Kaggle credentials that you can get from your Kaggle account settings. And then apply some setup so that Kaggle can be used from command line. And then downloading the dataset using that part of the URL that we copied previously. And finally unzipping the dataset to a folder called dataset. And I'll also be using weights and biases for logging the losses and progress of the generator. So we also need to install weights and biases and log in through it. So now let's start the actual implementation. So obviously first of all we need to import the required libraries. And also I'll be using G drive in order to save the checkpoints so that later I can resume my training. Now we need to create the dataset iterator and apply some transformation for augmentation and like general pre-processing of the data. And now I'm just gonna copy and paste two very useful visualization functions from my previous project and visualize some of these samples. And now we'll create a data loader and load a sample batch check its shape, and then finally visualize few samples from that batch. I think it's too big, so let me make it a bit smaller. Yep, looks very fine. So okay, now let's move on defining the generator, the actual architecture of the generator. And keep in mind that we'll be using that same points that we discussed earlier. So okay, let's carry on. So one detail I just like to point out that I won't be using sigmoid activation function as the discriminator's output, because I will be using binary cross entropy with logits as the loss. And the reason for that is this particular loss actually helps to prevent the loss becoming nan. So yeah. And now let's summarize the discriminator. So 11 million just for single model. Yeah, keep in mind that we're gonna have another model as the generator, so in training you have to have good amount of patience, otherwise you won't be able to get the best of the best that these both models can provide. And now moving to the generator. And finally summarizing the generator. So 30 million parameters. Okay. As a general suggestion, I'd like to say try to keep the generator weaker than the discriminator. And one of the easiest way for doing that is to have parameters in the generator less than parameters in the discriminator. But since in our case the dataset is kind of similar, like the overall structure of all the anime faces are still the same, like you have some sort of glitter on the cheeks and shine on the hairs and stuff, so I think it won't be too difficult for the discriminator to discriminate the generated samples. And now the initialization part, and yes, everything is taken from the paper, that the weights of the all convolution and deconvolution layer should be initialized for mean 0 and standard deviation 0.01. And for the batchnorm layer, the beta variable is supposed to be initialized with 0. And now defining the loss functions for both the discriminator and generator. And as I said, I'll be using binary cross entropy with logits, so let's carry on. Alright, so moving to the optimizers, and in paper they suggested to set the learning rate to 2e-4, but I'm gonna go with 4e-4, and in case something weird happens, then I'm gonna stop the training and I'll decrease the learning rate. Yeah. And keep in mind to set the beta 1 value for the RM optimizer to 0.5. You can try setting it to 0.45, but for now I'm just gonna go with this. And now finally I'm just gonna define few helper functions. So using these functions, if I want, I can carry on the training for a few days if required. and now a function to generate a random noise for the generator. So now I'll create a initial checkpoint before any kind of training and perform an initial load. And I almost forgot using the weights and biases, so yeah, let's set that up. And finally, let's code the training part. Alright, so the training has started, and we are logging everything from losses of both the models to the progress of the generator. So everything, we're gonna see everything in the weights and biases, and I'll see you when the training is done. Alright, so everything is done, and a lot of good news and a lot of bad news is there. So first of all, I'm very much satisfied with the final results. I personally was not hoping to get these good results, because I haven't done anything special. It's just a simple, very simple GAN. I just followed the guidelines from the paper, and here we go. So yeah, that's the good news. And the bad news is I screwed very much in the weights and biases. So I think maybe while resuming the training I did something wrong, and the logging of the generator's output as the training proceeds just got messed up. So like as you can see here, these high quality images aren't supposed to be here. I mean, they should be at the very end. And same goes for these losses, because I trained my GAN for more than 30 epochs, and per epoch I was logging the losses about 500 times. So after the training is done, I should have gotten at least 1500 logging steps. That is not the case. So anyways, let's see and visualize the generator's output in the notebook. So like here, as you can see, the generator was able to produce colorful hair, glittery eyes, and red cheeks and stuff. So yeah, I very much think that generator was successful at understanding the core feature of this particular dataset. Okay, so now let's move on to the fun part, that is the image interpolation, or you can say noise interpolation. So basically here what we do is you forces the generator to produce the outputs for not only two corresponding noise but also the interpolated noise between them. And using the image interpolation you can actually check if your generator is cheating or not. So in my case, these are the outputs, and I am again very much satisfied with the results. So as I haven't applied any special techniques like WGAN loss or LSGAN or gradient penalty or pixel norm and any of that, but still I'm able to get pretty good results. So one trick I like to share. So as I was training the model, I was continuously observing the produced images by the generator, and whenever I noticed something fishy is going on, so right there I stopped the training and reduced the learning rate. And yeah, finally here I am able to produce really good quality anime faces. Alright, I hope you learned something new and enjoyed the video. I'll see you around.